The Swiss Connection Science Podcast is back with brand new stories. They're all connected by one overarching theme: the climate challenges we face today and the smart solutions that can help us tackle them. This season we're diving into the depths of Swiss lakes, where invasive mussels are threatening the delicate indigenous ecosystem. We'll also travel to the Arctic to discover how ancient ice can reveal vital clues for pioneering climate research. And we'll explore the critical world of the semiconductor industry, looking at its global importance and Switzerland's potential role within it. All this and more is coming soon in the new season of the Swiss Connection Science Podcast. Swissinfo Podcasts.
Then the question is, where do you drill at a core where you find such old ice? And that's really not a simple feat. It's a really difficult task.
In the Antarctic, an international team of scientists has extracted an ice core that's 2,800 meters long.
This is probably around about 1.3 million years old, and this section is around about 1,200 years of climate history.
Within 150 years, we burned fossil fuel that nature took tens and hundreds of millions of years to create. Just by that we know how weather and climate was the last 30 years doesn't mean we know everything that the climate system is capable of.
Polar regions provide crucial insights into Earth's climate history. In the Antarctic, an international team of scientists has extracted an ice core that's 2,800 meters long. Researchers in Bern are now inspecting the ice, hoping to find answers to an unsolved mystery. Hello, I'm Jo Fay, and you're listening to the Swiss Connection Science Podcast. Today, we're going south to the Antarctic. We're at Little Dome C, a remote site on the Antarctic plateau near the French-Italian Concordia station. For over 4 years, researchers from 12 European scientific institutions, including the University of Bern in Switzerland, have been extracting ice cores here. The international team has been working here for more than 200 days, amid average summer temperatures of minus 35 degrees Celsius. In their 24-25 campaign, they drilled a 2,800-metre long ice core, reaching the bedrock beneath the Antarctic ice sheet. Some of these ice samples are now being scrutinised in Bern.
Hello, Luigi Swissinfo. Hi, how are you? Hi.
Hubertus Fischer, Professor of Experimental Climate Physics at the University of Bern, is a collaborator on the Beyond Epica project.
The story started more than 20 years ago when the international ice core community met during a workshop to define what are the major questions that we still have to address in the future. And one of the big riddles that we have to solve was the Mid-Pleistocene transition.
The Mid-Pleistocene transition, or MPT, poses one of the most complex mysteries in climate science. The Mid-Pleistocene refers to a key period within the Ice Age. During that period, between 900,000 and 1.2 million years ago, the extent of ice sheets in the Northern Hemisphere underwent drastic variations, with a deep impact on the climate. The interval between cold glacial and warm interglacial periods lengthened dramatically, from about 40,000 to 100,000 years, and the amount of ice on Earth during glacial times dramatically increased. CO2 is one of the major parameters to measure to find out what the reason is for this mid-Pleistocene transition. And to find out about CO2 air levels of the past, you can look at air bubbles trapped inside old ice. This European group already drilled for ice around the turn of the millennium. The Epica project, as it was called then, already revealed atmospheric carbon dioxide concentrations of the past 800,000 years. The Beyond Epica project will now go back into 1.2 million years of climate history.
Then the question is, where do you drill at a core where you find such old ice? And that's really not a simple feat. It's a really difficult task. So we had a first EU project where we for 3 years went into the field. We did glaciological studies, geophysical studies of the ice sheet to look into the ice itself in order to find a drill site which promises us such old ice. We identified one of those. This was the drill site that we are now drilling at Little Dome C.
Hubertus has not been on the Little Dome C site himself, but he knows those working conditions from previous Antarctic missions he worked on.
First of all, it's really cold. I mean, you're talking about minus 30 degrees in summer. You can protect yourself very well against cold with white clothing, but I think the one limitation is the fingers, because you have to still do work and many things need fine manipulation, so you cannot have thick gloves on all the time. And I personally get cold fingers very well. I once froze my fingertips in Antarctica, and since then it's even worse. So I get cold fingers very, very quickly. You are in the middle of nowhere in a camp with maybe 15 other persons in Little Dome C. There is a heated room where you have a kitchen where someone is cooking for you. There are containers where you can sleep in, or if you want it also in a tent, but it's very cold. There's a shower, a toilet container and stuff like this. But still, it's in the middle of nowhere. You have to get along with your colleagues, 15 people over 3 months. You're away from everywhere. And there's very little stimulus outside of the camp. You have to imagine you're standing on the glacier, which is snow. It's absolutely flat to the horizon. There are no mountains that you can see. There's just the sky, which slowly changes. And you have to appreciate those small differences, like changes in the snow surface, in crystals in the atmosphere. You see sometimes halos or other light effects.
So let's move to a slightly warmer place, over to Switzerland. Our science journalists, Luigi Iorio and Michele Andina, have visited the University of Bern to find out what's happening to those ice samples now. Michele, tell us what you discovered.
Yes, of course. I should mention that other European institutes involved in the Beyond Epica project are also analysing samples, not just Bern. They all have their special expertise, but Bern has specialised in looking at greenhouse gases in this highly compressed, very old ice.
Yeah, and if you're feeling too cold or whatever, we can take a break.
So here in Bern, we met with climate researcher Florian Kraus, who himself has worked on the Little Dome C drilling site in Antarctica.
Yeah, put on some gloves.
He first took us inside their minus 50 degrees cold chamber, where they store the samples.
I just need to get our sample container.
So you put your ice in the ice cream box.
Yeah, exactly. We have this this ice cream box with some cooling packs. Okay, ready? Please close the door behind you.
Dressed in warm jackets, gloves and hats, we enter the room and immediately get a sense of what it must be like working in the Antarctic. At first, I find it painful to breathe. Florian's hair and moustache quickly turn white with frost. There are 30 or 40 plastic cases stored here, all containing ice from the Antarctic. Florian opens one of the cases.
So this is the box with the samples that I'm analyzing. I kind of sorted the samples already, so it should be not too hard to find them. So you can see that there's already many 10 centimeter pieces. This is how the sample looks like. And this is the ice coming from 2.5 kilometers deep.
Each sample, cut into a 10 centimeter block, is wrapped up separately in a labeled plastic bag.
This is probably around about 1.3 million years old. And this section, just this section, is around about 1,200 years of climate history. Good, then we go to the cutting room.
Yep.
Florian puts the sample into his ice cream box to keep it cool while taking it to the cutting room, another cold room equipped with a bandsaw.
I'm preparing the saw now, and then what we gonna do is that we decontaminate the outer sides of the ice core sample because the outer sides were in contact with gloves, with the plastic bag, maybe also with some drilling fluid at some point if it has micro cracks. So we don't know. And to reduce the effect of anything that is kind of stuck at the ice, we need to remove the outer sides. But of course, as little as possible, because I don't want to waste any sample. It's so precious that I don't want to waste any kind of sample.
Next to the saw, Florian keeps a sheet of paper with an arrow drawn on. Whenever he turns the sample, he also turns the paper with the arrow, in order not to lose track of what's the top and what's the bottom part of the ice block. This is crucial. At every step of the process, from the extraction of the core from the Antarctic ice sheet, to cutting it into smaller samples and packing them into plastic bags, to the processing in the lab, the researchers must always know what the top and what the bottom of their sample is. Even with only a 10 centimeter sample, getting this mixed up can lead to errors of plus or minus 1,200 years. There are arrows carved onto the sample, and the sample bags are also labeled with arrows. Now it's time to release the ancient air.
Okay.
To do this, the researchers in Bern have developed a special machine with a laser.
So what we do next is that we place the ice core sample in the extraction vessel. Again, top to the top.
The extraction vessel is a container made of stainless steel, coated with gold.
Looks good. And tighten all the screws again.
Once the ice block is nicely positioned inside, Florian closes the lid, which is a metal frame with a glass window for the laser to shine through. Everything's cooled with liquid nitrogen.
What the system is doing now is that it's first of all pumping the extraction vessel for half an hour with the membrane pump. Following to this, it switches to the turbo pump to reach really high vacuum. And at the same time, the whole system is cooled down to minus 100 degrees.
And now it's time to melt the ice. Or actually, I should say to sublimate the ice. Sublimation is the process of turning ice from its solid state directly into gas, skipping the liquid phase. The absence of a liquid phase prevents any released CO2 from dissolving in water, which could alter the results.
The laser beam shoots on the ice core sample, and at this wavelength, the laser itself penetrates the ice only in a sub-millimeter range. That means we have a smooth sublimation front from the top to the bottom, and it takes around about 20 minutes for 1.5 centimeters of ice to sublimate. And the air is released within the extraction vessel. However, since the extraction vessel itself is so cold, the water vapor that is emerging is frozen out on the side.
Okay.
This temperature is, however, not low enough to also freeze out all the gases. So the gas is pretty much following a pressure gradient into so-called dip tubes. I can show you here on the other side. This is how one dip tube, one finger looks like. So it's pretty much just a valve and a hollow pole, more or less. And this sticks in a cryostat. And this cryostat is at 15 Kelvin right now. So it's really, really cold. 15 Kelvin right now. And at these temperatures, you freeze out the gases.
Okay.
And the gas is pretty much just following the pressure gradient from the extraction vessel into the dip tubes.
Why you need to freeze the gases?
Because we want to trap it. We want to trap it, and we want to have a pressure gradient within the system to suck the sample out of the extraction vessel. And the temperature gradient from the extraction vessel having minus 100 degrees and the dip tubes having 15 Kelvin literally is enough to suck the sample into the fingers and freeze it out. And after the measurement, I'm going to close the valve, and the sample itself, so the bulk air sample, is trapped in the fingers.
Okay.
And these fingers are then afterwards analyzed in a laser spectrometer.
Okay. Okay. And there you can see what kind of gases.
Exactly. And there I pretty much quantify the concentration of the gases of CO2, methane, N2O, but also of isotopes of CO2.
What do you expect to find in this sample?
In this sample, I probably expect to find rather low CO2 concentrations because it's probably not an interglacial, so maybe roughly 220, 230 ppm. like this.
Some of us that what we have today, right?
Exactly.
These ice samples will keep the researchers busy for several years now. But eventually, they should reveal what happened during the Mid-Pleistocene and provide a clear picture of the Earth's climate 1.2, 1.3, perhaps even 1.5 million years ago. But what about the time before that? Is there even older ice that could potentially be found, perhaps in future missions? Luigi asked Hubertus Fischer about exactly that.
I don't think with a continuous ice core like this one that we will be able to go much more than the 1.5 million years. The reason is you need relatively thick ice in order to be able to still have enough ice of the section that you're interested in. So you get the necessary resolution. But if the ice gets too thick, then because of the geothermal heat flux at the bottom of the ice becomes warmer with depth. And the more ice you have, the more insulation you have, the warmer the ice at the bottom gets. And if you get over 2,800 meters, then the ice starts to melt at the bottom. Okay. And when it melts at the bottom, all the old ice is gone. It melts away. Okay. So there is a physical limitation to how old you can really find ice in Antarctica, given that there's a certain geothermal heat flux and a certain temperature at the surface. But there are other ways to get even older ice, and it is going to the outcropping at the coast, where very old ice, the ice is created in the middle of the ice sheet and it flows down and it flows to the coast. Okay. That's how a glacier works. It accumulates at some point and it flows, and then at the coast it breaks off as a table iceberg. And colleagues in the US, they went to coastal sites where they actually were able to find ice 4 million years old. But the thing is, this ice is not in a continuous sequence. So you find kind of a patch of ice, and you have to date it, and then you know, oh, it's 4 million years plus minus maybe 100,000. And then you can measure what's in there. Yeah. But this means already 4 million plus minus 100,000, you don't know, is this glacial ice or interglacial ice? So you get snapshots, but you don't get a continuous record. And then, of course, there are limitations to what you can do in terms of climate interpretation.
Why it's important to extract and to study the ice from Antarctica?
The issue is that direct observations that we have about climate or greenhouse gases are very limited in terms of time. We can reconstruct from direct observations global temperatures maybe over the last 150 years. For greenhouse gases, the CO2 record for Mauna Loa starts in 1958. That's where CO2 was already significantly elevated over the pre-industrial background. Methane records we only have since the mid-1980s, so the last 40 years. And that's where methane was already high, sky high. So to really understand what the natural condition is of our planet, we have to go further back in time. And climate archives, natural climate archives, provide us with this information. And the ice cores are very special because they are the only archive where you can measure the atmospheric composition. Another example, current hot topic are tipping points. The tipping points really, again, I would say, are a result from ice core research. And that ice core research was in Greenland, where we drilled deep ice cores. And in the last glacial, one found these very rapid climate variations called Danskar-Oeschger events. I don't know whether you ever heard about them. So in the last glacial in Greenland, there were warmings on the order of 10 to 15 degrees in 100 years. Locally in Greenland. It's not a global signal, but that's a size of climate change where our current climate change is really small compared to this. But it's a local phenomenon and has to do with this concept of the Atlantic meridional overturning circulation, AMOC, which is the heat pump transporting heat from lower latitudes to high latitudes. And this warm ocean stream is, for example, also important for our European climate. If you look, for example, to Scandinavia, temperatures are relatively mild. If you go to the same latitude as Scandinavia, for example, in North America, it's much colder. It's because there is not this ocean heat pump which makes the climate so much milder. And if this heat pump shuts off, then suddenly it's getting much colder, and when this heat pump switches on, it gets much warmer in the North Atlantic. And that's what's leading to those very rapid warmings in Greenland. Whenever in the glacial, this heat pump switched on, it suddenly got warmer by 10 to 15 degrees, also amplified by sea ice and stuff. And before that, people didn't even think that our climate system is able to do such rapid and drastic variations. We have this picture, an ice age, warm age, takes 10,000 of years to go from an ice age to a warm age. And so you see that the dynamic of our climate system is much more diverse. And again, if you don't have this extended window of observations by natural climate archives like ice cores, you will never be able to see this. But now this thing about EMOC is very high on the agenda, because people say maybe this heat pump will shut off in this century, in the course of this century, maybe not. Maybe it's just getting weaker, but others say it might completely collapse. And again, a concept which has only been recognized because of ice core research.
Is there like a message that ancient ice science can send to policymakers?
I mean, one of the messages that I hammer in is always that we are way above natural conditions in terms of greenhouse gases. And that in terms of CO2, there were no times in the past which were changing CO2 as fast and as sustained over 150 years. We have exponential growth. So the natural climate system is not able to do that. But humankind was able to do it. I mean, within 150 years, we burned fossil fuel that nature took tens of millions of millions of years to create all those fossil fuel storages, oil storages, coal storage, and so on. So it's really incredible what humankind is doing. And unfortunately, there are so many examples. We do something and we only start to switch on our brain afterwards and think about the consequences. Just by that we know how weather and climate was the last 30 years doesn't mean we know everything that the climate system is capable of. So we should be a little bit more careful, not a little bit, we should be much more careful and not assume everything stays the same and everything happens slowly. In fact, the current climate change is so fast that it's not the planet Earth that cannot handle this. I mean, climate will change areas, there will be desertification in certain areas, ecosystems will move, Scandinavia will be much warmer, Italy will be much drier, Switzerland will be drier in summer but more rain in the winter, so we will have to adjust too. Yes, organisms would die in some area, they would move, others may be even extinct. But the problem is that our highly interconnected societies, with now 8, close to 9 billion people on this planet, we as human species cannot adapt fast enough. And there will be people who will lose their livelihood and their well-being because of climate change. This is clear. Already just because of the sea level change, many of the places, the coasts are the most populated areas, people have to move or you have to install technical protections, and how much money do you have to invest? So there will be consequences, there are already consequences. And examples from the past can help us get a better grip on that, what is possible.
Thank you, Michele, for sharing that story with us. So when will we get the full picture of what happened during the Mid-Pleistocene transition and of our climate 1.2 million years ago?
Well, I just contacted Hubertus to see where they currently stand. They're still working on it, but he expects to have some first results this summer. However, that's only the first results, and it will take several more years to complete the picture. Also, drilling for more ice will continue for another season or so. The goal is to get more ice to measure other parameters, since most of the ice from the main core is already used.
Okay, so thank you very much, and we'll try to come back to this story at a later time then.
Yeah, I hope so.
And also many thanks to our colleague Luigi Iorio, who you heard in that report. In our next episode of the Swiss Connection Science podcast, we'll visit the Hunziker Areal. That's a neighbourhood of modern houses built over 10 years ago. It was planned to be a model of low-energy housing and a social experiment. If you missed any of our earlier episodes on longevity, you can scroll back in your feed and have a listen to our last season. It's highly recommended. For more science stories, visit our website, swissinfo.ch. And you can help other people to find our fabulous podcast by leaving us a 5-star review wherever you get your podcast, or you can tell a friend. Today's episode was recorded and edited by our science and video journalist Michele Andina. For more content, check out our website, swissinfo.ch. I'm Jo Fay. Thanks for listening. Hello, this is Jo Fay from the Swiss Connection Science podcast. You're about to hear our new investigative podcast series, Lost Cells. It weaves together personal accounts from families in Spain, Serbia, Italy and beyond as they deal with the promises and failures of private stem cell banking. It's a global story with Switzerland at its heart. I hope you enjoy listening to it.